Benzene has an unusual stability because it is aromatic. There are three terms that we want to define: aromatic, anti-aromatic, and non-aromatic. For the stability, always aromatic compounds, they are way more stable than non-aromatic compounds, than anti-aromatic compounds. Each one of those, they go with their own rule, and you have to memorize those rules in there. So for a compound to be aromatic, this is called the Huckel's rule. The compound should be cyclic and should be planar. By planar, we mean that all carbons, they need to be in the same plane, having an sp2 hybridization. So in this case, we will have all the p orbitals overlapping with each other. So if your compound is planar, then this is the same thing as conjugated. So planar means that it is a conjugated system, meaning that all the p orbitals, they lie in the same plane. And then you go by the number of electrons in there. Aromatic follows the number of electrons to be 4n plus 2, where n is an integer. Now you don't have to calculate the n. N is just an integer in there, but the number of electrons, you have to find it from the structure. Remember that every double bond is a 2 electron. So if your number of electrons is any of those, go plus 4 as you go. Then in this case, together with the conditions listed above, then in this case your compound is going to be aromatic. If your compound is anti-aromatic, then it should be cyclic and planar. So the same two conditions for the aromatic, they are for the anti-aromatic. They just differ in the number of electrons. The number of electrons here follows the 4n rule, not the 4n plus 2 rule. N is still an integer. And the number of electrons, you can find it from the structure. Again, every double bond is a 2 electron. So you're going by 4, 8, 12, add a plus 4 as you go. So if the number of electrons here is different than the number of electrons here, then the compound is going to be anti-aromatic. The last case is for the non-aromatic. The non-aromatic, the compound is either not cyclic or not planar, with different number of electrons. So it can be any of the 4n plus 2 electrons, or any of the 4n electrons in there, or even an odd number of electrons. We get the odd number of electrons whenever we have a free radical. So the moment you see a free radical, this is going to be immediately a non-aromatic structure. Non-aromatics, they are more stable than anti-aromatics. Anti-aromatics are the least stable. Let's have an example. Benzene. Benzene. Benzene is cyclic. All its carbons are sp2 hybridization. So it is planar, and you can see that the p orbitals overlap with each other, so they lie in the same plane. This means that your system is conjugated. The number of electrons, count every double bond is a 2 electron, and you're going to end up with 6 pi electrons. So all of these conditions, they do satisfy an aromatic compound. This is why we say that benzene is aromatic. On the other end, if you look at the cyclobutadiene, cyclobutadiene is still cyclic. It is still planar in there. All the p orbitals, they lie in the same plane. However, the number of electrons is a 4 pi electron. Each double bond is a 2 electron. So this is going to be a condition for anti-aromatic structure. There are two cyclic molecules in there that we're going to consider as an exception: an 8 carbon cycle and a 10 carbon cycle. If you look at the 8 carbon cycle, it seems that it is planar, but if you draw it as a puckered conformation, then the p orbitals are not in the same plane. These two p orbitals, they overlap with each other, and these two p orbitals, they overlap with each other. But because the carbons are not in the same plane, there is no overlapping between those p orbitals in there. So since there is no overlapping between the p orbitals, we say that the structure is not planar. It is not conjugated. And if it is not conjugated, even though it's a cyclic structure, it has 8 electrons in this case, that is considered to be a non-aromatic structure. So if it is non-aromatic, this means that the double bonds are in different plane. And if they are in different plane and I want to do a bromination, for example, then I'm going to treat each double bond separate. Treating each double bond separate, I'm just going to brominate based on the number of moles that I have. So if I have 1 mole, I'm going to brominate just one double bond. 2 moles, I'm going to do 2 of them, and as you go. The other exception is a cycle of 10 carbons. If you represent it as a puckered conformation, then in this case, you would see that we have two trans hydrogens. And those trans hydrogens, you want to make them as far away as possible from each other so that there is no repulsion between them. These hydrogens are in different planes, so the p orbitals of this side of the cycle are in different plane with the p orbitals of the other side of the cycle. So there is no conjugation, no planar structure. It's just cyclic with the number of electrons here being 10 pi electrons. So again, the compound is a non-aromatic structure. If we have aromatic rings that are more than 10 carbons, so 10 carbons is not aromatic. So for rings that are more than 10 carbons and they are conjugated, these are considered to be aromatic. And we name those as anilines. Anilines have single and double bonds alternating. And in order to name anilines, this is how we draw the anilines in there. And in order to name anilines, there are two ways to do that. It's either by counting all the carbon in the structure, and here in this case, we have 14 carbons. So you put it in brackets, and then you put the name aniline at the end. Or you count the number of electrons. Here I do have 7 double bonds. So it is going to be a 14 electron and you put it in a bracket. So either you go by the name, the number of carbons, or you go by the number of electrons. And both are going to be the same. The 10 carbon structure, it is not conjugated, but we still name it as an aniline because it does have an alternation of a double and a single bond. There are 3 structures that you are responsible for. Naphthalene is whenever you have 2 benzenes that are fused together. Anthracene and phenanthrene, these are 3 benzenes fused together at different positions. Whenever you want to represent all of those, instead of showing all the double bonds, you can show simple circles inside the benzene in there, showing that the double bonds can be anywhere on the benzene because after all, these are conjugated systems. All of the all of the fused aromatic rings, they undergo resonance, and as the number of fused rings increase, as the resonance structures increase. This is an example over here of the different resonance structures of the naphthalene, and naphthalene is always represented by its hybrid structure. It's not just hydrocarbons that are considered to be aromatic. Also, heterocycles are considered to be aromatic. But you just want to know where the lone pairs of the heterocycle reside, either in the p orbital or in the hybrid orbital. So, cycles that contain oxygen, nitrogen, or sulfur, they can also be aromatic. And always, whenever figuring the number of electrons in the cycle, you always need to check the lone pairs and where the lone pairs are in the cycle. Are they in the cycle or outside the cycle? If they are in the cycle, this means that they belong to the p orbital, they are involved in resonance. So you need to count them when counting the number of electrons. If they are outside the cycle, this means that they are in the hybrid orbital. Those, they are not involved in resonance, and you cannot count them when you're counting the number of electrons. Let's have an example in there. All the carbons and the nitrogen is an sp2 hybridization. The nitrogen is an sp2 hybridization because the nitrogen has 1, 2, and 3 groups around it. So it has 3 groups around it. It's an sp2 hybridization in there. These lone pairs, they do belong to the sp2 orbital because the p orbital of the nitrogen is already occupied with the one electron that is overlapping with this carbon to make the pi bond. That is going to push the lone pairs outside the cycle. So when we are counting the number of electrons in the cycle, we cannot count those lone pairs because those lone pairs, they don't belong to the p. The p is already occupied with electrons, and there's an overlap of the p orbitals in there above the ring and below the ring. So that is going to create an electron density in there, and the lone pairs now, they do belong to the hybrid orbital. That is going to make pyridine to be basic. So if you want to consider lone pairs, if they are basic or not, look where they belong. If they belong to the p orbital, this means that they are involved in conjugation. They cannot be a base. Because remember the definition of the base. You're using the lone pairs in order to make a bond with the acid. So those lone pairs, they have to be free lone pairs. They cannot be conjugated. If they are conjugated, then you cannot use them to make bonds with acids, with acidic hydrogens in there. These lone pairs, they are now free to bond with acidic hydrogens. So this is why we're going to consider pyridine as a basic structure. Pyridine is now cyclic, it is planar, it has 6 pi electrons, so it is aromatic and it is very stable. On the other end, if you consider pyrrole now, pyrrole has, see how many groups there are around the nitrogen. It's 1, 2, and 3 groups. You don't count the lone pairs as a group because the lone pairs are conjugated with the double bond. If you have the choice to do resonance inside the structure by using the lone pairs, then put the lone pairs in the p orbital. So here the lone pairs are going to be in the p orbital, and we said that the capacity of the p orbital is a max of 2 electrons. So that is going to make the nitrogen an sp2 hybridization. So your structure now is an sp2 for all its elements. So now it's going to be planar. It is conjugated because all the p orbitals, they overlap with each other. It is cyclic, so now it's considered to be aromatic. If I want to consider the basicity of the pyrrole, is the pyrrole basic? So here is pyrrole basic. Then all what I need to do is look at the position of the lone pair and see where is the lone pair. For the lone pairs, or for the structure to be basic, the lone pairs, they do need to belong to the hybrid orbital, not to the p orbital. If the lone pairs belong to the p orbital, as we said before, then those lone pairs will be involved in conjugation. They will not be involved to make a bond with the acidic hydrogen. So this is why we consider pyrrole as a weak base. So pyrrole is not basic. Let's have more examples. So the question here, are these lone pairs basic? So as we said, that lone pairs to be basic, they have to belong to the hybrid orbital. Whether the hybrid orbital is an sp2 hybridization or it's an sp3 hybridization, then they can be involved in making new sigma bonds with the acidic hydrogen. If the lone pairs, they belong to the p orbital, then in this case, the lone pairs are going to be, or the structure is going to be non-basic. If they belong to the hybrid orbital, then the lone pairs are going to be basic. So let's have an example in here. If the lone pairs are involved in resonance, then in this case, those lone pairs, they belong to the p orbital. So that is going to make the lone pairs non-basic. On the other hand, these lone pairs, there is no conjugation around them. So these lone pairs, they have to belong to a hybrid orbital. So now if I consider the hybridization of this nitrogen has four groups around it. One, two, three, and four. So if it has four groups around it, then it is an sp3 hybridization. Because the lone pairs belong to the hybrid orbital, then these lone pairs are considered to be basic. Same thing in here. If there is a conjugated system next to the lone pair, then these lone pairs will belong to the p orbital. This is going to make the hybridization of this nitrogen an sp2 hybridization, and it's going to make those lone pairs non-basic. These lone pairs now over here, because the conjugation is so far away, then I can make those lone pairs in the hybrid orbital, and the hybridization of this nitrogen now is going to be in the sp3, and those lone pairs are going to be basic. Anions. Aromatic compounds can also be ionic, either carrying a plus charge or a negative charge. If they carry a negative charge, we call it anions. And to make anions, you simply start with your cycle in there, and you use a base. And that base is going to come and take the allylic hydrogen, which is the most acidic hydrogen, because it belongs to an sp3 hybrid carbon, and it's easy to break any of those sigma bonds. So when the base comes and takes the acidic hydrogen, then you're going to create your anion in there. You are responsible to name those anions. These go by the same name as the original structure. And to do that, name the hydrocarbon. We drop the E in the hydrocarbon and we add a YL and then the identity of the ion that you are making. If it is a negative charge, then it's going to be an anion. If it's a positive charge, then it's going to be a cation. Now, in this case, you started with a non-aromatic structure because it is non-planar, and you ended up with an aromatic structure. This aromatic structure has a lone pairs around the carbon, and these lone pairs, they belong to the p orbital. So this is why you do have a conjugation in there around the p orbital. It's going to make those lone pairs non-basic though, because those lone pairs, they belong to the p orbital in here. But the structure is going to be stable and is going to be aromatic. Base reaction here. You always look at your conjugate base and see if your conjugate base is stable, then your structure is going to be acidic. And that explains why this hydrogen is a slightly an acidic hydrogen, because its conjugate base is stable due to resonance. These are the 5 resonance structures of the cyclopentadienyl anion, where it shows that the negative charge is alternating over all the carbons in there. So I have 5 carbons. The negative charge is going to be on each one of them, so I'm going to end up having 5 resonance structures. Now, to make a cation, you have to do a dehydration reaction, and you have to start with an alcohol. This is a secondary alcohol, so you are doing an E1 elimination, where water needs to leave to create a carbocation. And this is how you make cations in there. So the tropylium cation, this is a cycle of 7 carbons. It is not planar. It is not aromatic. And the reason why it's not planar, because there is one sp3 hybrid carbon. It's enough to have one carbon that is not sp2 in the structure to make the structure not planar. So if it is not planar, then immediately it's going to be not aromatic, even though it satisfies the number of electrons here, which is a 6 pi electron, but the structure has one sp3 hybrid carbon, so it is not planar in this case. Once you do its cation is going to be stable. It is aromatic because all the carbons in there are sp2 hybridization, and you do have a conjugation in there around the p orbitals. So the electrons around the p orbitals, they hop from one p orbital to the other, and there is a place for them in this empty p orbital. So that makes the tropylium cation an aromatic structure, and it is stable by resonance. If it's stable by resonance, you need to show its resonance structures where the plus charge is moving over every single carbon. Since you have 7 carbons, you're going to end up having 7 resonance structures in this case. Again, if you start moving from one direction, just go ahead and make your resonance structures move in the same direction so that you can alternate that positive charge and move it across the carbons of the cycle.